All right, we're starting up chapter 5 on probability. I want to make a quick note. I just looked at homework and 6 people have done the chapter 2 review homework for the review homework for chapter 2, which we finished lecturing on like fucking over 2 weeks ago. You guys, if you don't get caught up on the homework, you're gonna have a really fucking hard time getting it done before the midterm, and the midterm is gonna run you over like a train. Okay, you guys gotta get caught up. I'm not gonna point fingers, I'm not gonna name names, some of you are on top of it, some of you are ahead. I saw some people, a couple of people had chapters and stuff done in chapter 5. Alright, so. Chapter 5, this is not a computer chapter, this is a calculator chapter. There is no stat crunch involved for chapter 5. So what is probability? Probability is the long-term proportion in which a certain outcome is observed in situations with short-term uncertainty. Is everybody familiar with a standard deck of playing cards? If you're not, it's fine. Has anyone never used a deck of cards, like something that's got these in it? Everyone's used them? No one's, this is nothing new? Okay, good. There are 4 suits. Diamonds, spades, clubs, and hearts. Each suit has 13 cards in it. Ace, king, queen, jack, 10, and then 2 through 9. And so there's a total of 52 cards in the deck. We use decks of cards a lot for probability. It's one of the most easiest things to do because the probability is fixed. But here's an example of what probability is. Since there are 4 different colors, or not colors, but 4 different suits. And so that's it's a little bit random.
Are you gonna show us how to gamble?
Not today, but yes. Or at least a little bit. We'll talk about roulette, we'll talk about Texas Hold'em. Alright, so 4 suits. Deck of, they're called playing cards. I'm gonna say standard playing cards, because in today's world. If I say playing cards or cards, someone's probably gonna think Magic the Gathering or Pokemon or some shit like that. 4 suits. They're called ranks, there's 13 ranks in each suit. We have our hearts and our diamonds. We have our spades and we have our clubs. Ace, king, queen, jack, 10. And then 9 down to 2. The probability of drawing. What's your favorite suit, Amar?
Subs.
The fuck, no one likes clubs. Probability of drawing a club is 1/4.
It's going to be so many, so I gotta like.
Yeah, I gotta approve of that. That is a long-term outcome. If I draw 3 cards, I'll draw them at random, I've been shuffling them. No, we'll do 4 cards. We managed to get 1/4 on clubs. I got 1 club out of 4 cards. Such that just happened to be chance. Notice that this probability is the same for all the suits. But on the hearts, I got 2 clubs out of 4, which would have been 1/2. And on spades, I didn't get any spades. So there's short-term uncertainty on what suit I'm gonna get. But in the long-term thing, if you draw 1,000 cards, approximately 1/4 of them are gonna be clubs. That's what we mean by probability. We use the card form here. Another way of thinking it is it's a probability is the measure. Of the likelihood. Of a random event or phenomenon occurring. Phenomenon. I think that's how you spell it. I don't know. Now it looks funny. Phenomenon. Fuck it.
Let's. Now, nice.
What, let's see. Go fucking find phenomenon. It doesn't even sound right when I say it now. Phenomenon. Nope, so in. Yeah, it looked kind of funny. Or phenomenon occurring. Alright, we're gonna get some other. So. When I drew the 4 cards. I drew 4 cards, those are called trials. So the proportion that I drew. For hearts, I had 2/4, which is 1/2. For diamonds, I had 1/4. For clubs, 1/4. For spades. 0. Or 0/4. These are proportions, it's the proportion I drew, it's not probability here. Proportion and probability have a very strong connection. As I increase the number of trials. We'll say n number of trials to a large number. These proportions will approach the true probability. So I got 0 spades, but if I draw 100 cards, I'm gonna get around 25 spades. I might get 26, I might get 27. But if I look at a decimal, there, whatever I get is probably gonna be pretty close to 0.25, which is 1/4. We're gonna look at an actual live, we're gonna do an experiment in class today. We're gonna shift the lecture around, we're only gonna do 5.1 today, I wanna. Do an activity with you guys to like really lock this shit in. There's a lot of questions on the midterm on probability, because it's a big chapter, it's an important chapter. So there's some key terms in this topic. There's always definitions we need to learn. One is sample space. We often use the letter S to describe it. It is the set of all possible outcomes. An event. Is a collection of one or more outcomes. This usually goes by the letter E, sometimes F if we need a second letter. And when they list the outcomes, they might use E. Lowercase e with an I for the different outcomes. In an event. We have some rules for probability. Not a lot. Well, there's more, but the basic rules are these. The probability of event E occurring. And we say it as this P parentheses E. Probability of event E is P parentheses E. Is between 0 and 1. Zero is less than or equal to the probability of event E, which is less than or equal to 1. And B, the sum of the probabilities of independent events is 1. Here, we're gonna do the summation materials, symbol. And I'm gonna use EI, not big E. Because. I'll show you an example. Events can be. Related, and so it won't work that way.
An equal sign?
That is an equal sign. Usually, if we don't wanna, if we wanna be more specific with what our event is. We are gonna not use a letter, but like, say what it is. The probability of drawing a spade. Is 1/4. The probability of getting a heart is 1/4. The probability of getting a club is 1/4. And the probability of a diamond is 1/4. These are all independent events. And we'll go over more about independent events next week, but the idea is. Outcomes in one event are not in any of the others. So if I draw a spade, it is not a club, it is not a diamond, it is not a heart. Those represent all 4 suits. So if I add them up. Here I'm using the symbols now, let's speed this up a little bit. This is 1/4 plus 1/4 plus 1/4 plus 1/4. That adds up to 4/4, which is 1. Now, these events have to be independent. The probability of drawing a black card. Is 1/2. And the probability of drawing a red card. Is 1/2. Each of these have 26 cards out of a total of 52. These two add up to 1 also. 1/2 plus 1/2 equals 1. If I try to say probability of a spade. Plus the probability of. Heart. And diamond. And a black heart. This is 1/4 plus 1/4. Plus 1/4 plus 2/4. Gets us 5/4. This is bigger than 1, but. These events were not independent. So they have to be independent events to add up to one. And you have to have all of the events. Spades are. In the. Color black. So when I count a spade, I'm counting in both categories. And we'll see what happens when we have things, these are called dependent events. And we'll see how to address this later on. There's a way to make it so it still adds up to one. Okay, so. Some called the probability model. This is usually listed or given as a table. And it must. Satisfy those two criteria. Those two rules. To be a probability model. Probability of any event is between 0 and 1. And if we add up all the individual outcomes. The probability should equal 1. That's the requirement right there. This is handy. This means no negative values. No values greater than 1. Everything should start with 0 point something. This next thing comes up a lot, so I'm gonna draw a table so that we can come up with a probability model. Let's make the probability model for the sum of two dice. Fun fact, singular is die. One die or plural is dice. So I'm gonna use like a regular good old 6-sided. Standard die. That kind of thing. So I'll make a table. I'm gonna make a chart depicting what they are so we can add them up. So this is, I'm gonna use two different colors too. I'll use black and red, so I've got a black die and a red die. I can have on the black die, I could have a 1, I could have a 2. I could have a 3. I could have a 4. I could have a 5 show up on top. Or I could have a 6. And I'll make the same picture going down the left side. So if I add up the faces on the dots on them, another fun fact. Dots on dice are called pips.
Yes.
PIP, pips.
Thanks.
You'll see it follows a pattern. If you go across any individual row, it just increases by 1. So you just gotta figure out what the first one is and then just keep adding 1. 1 plus 2 is 3, so this goes like this. So we're gonna use that in a second. I was saying 1/4 of the probability. I didn't give you I'm gonna give you a little more information about probability. Probability of E is like, the frequency of E. Over, like the total number of trials. Frequency of E occurring. Which kind of makes it like relative frequency. That's a tie back to a previous chapter. There's another way they list this, they say N and E. Over N and S. This is number of ways E it can occur. And this is. Number. Total outcomes. In S. The entire sentence list. This latter one, this blue one tends to be, is for the classical method. The classical method is when. The probability of, or the outcomes are equally likely to occur. So like the probability of getting any specific combination. Like 2. On the red die and 1 on the black die. There's only one combination out of a total of 36 combinations. And you can count them out and see there's 36. We'll see another way to get that 36 other than counting in a second. This top one tends to be for experimental. Or often called empirical method. We're gonna do that today too. In something where the outcome is not known. And there is no way of getting it other than just doing repeated experiments. I put relative frequency here, I'm gonna say looks like relative frequency. It's the same equation, it's not the same thing. And we'll go over the difference in a second. Actually, I'll do it now. How do relative frequency and probability differ? Relative frequency. Measures. How often an event. Occurred. During a unit of time. Or over a specific number of trials. Probability, despite having a similar formula. Is the likelihood. Of an unknown or of an event occurring. When the outcome is unknown. And after you've written that down, there's a very clear cut, like everyone should be able to grasp this. in a second when I. Break it down into 2 words. But I wanna make sure everyone's done writing and then focus on it. Oh, and frequency occurred in the past. Probability is something that you're talking about, something that hasn't happened yet, it's the future. That's an easy way to distinguish it. This thing where I said classical method here. Almost every single casino game is based off this. Casino games with dice and cards are based off this. Not like if they have a betting track or, you know. They're betting on horse races or fucking football or shit like that, that's different. That's got unknown variables in it, but games with dice and cards are all determined with classical method. Let's make our probability model for our table here. Let's see, maybe let me do this. That'll work. Side by side, look at that, bam, it just barely fits. So it looks like we're doing the sum, which is the numbers I have in blue. So the sum, and I will put the probability of that sum. Make a table. I see numbers from 2 to 12. And I'm putting cross lines in because otherwise these things are gonna start to blur what's what. How many different ways can I get a 2? There's just one, right? There are 36 outcomes, so the probability of getting a 2 is 1/36. One outcome over 36 total. All of these will have a denominator of 36. We can always, not always, but in some cases, simplify this. Make a smaller fraction. But I'm not going to because I think it's a little easier to see what's going on here. How many ways can I get a 3? Two, right? You'll notice numbers, the sums occur along a diagonal. So you go along a diagonal, that diagonal all has the same values. So there's 2 ways to get a 3. If we look at the 4. There's 3 ways to get a 4. There's 4 ways to get a 5, and there's 5 ways to get a 6. 7 has the most, 7 has 6 different ways. This might look a little bit better if I do like a diagonal like that. It might be a little bit easier to read. And then when we get to 8, the numbers start going back down again.
1 second.
So the way to read that is like the probability that the sum equals a 6 is 5/36. You could shorten this to just saying probability 6. But if you have sum there, it's clear you're talking about that you added up the dice. Whereas 6 is actually an outcome on one of the dice, so that might be confusing. So if we add these up. And they all have a common denominator. If I add up the probability of my different sums. I've got. It's all one big fraction. Since it's got the same denominator, I can just do it as 1. 1 plus 2, I'm just adding these numbers up, the numerators. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. How many do we get when we add up the numbers on top? Well. These two make a 6. These two make a 6. These two make a 6, these two make a 6. That's 4 6s so far, here's a 6, that's 5 6s. And then the 2 3s make another 6, so there's 6 different 6s. 6 times 6 on top is 36. Over 36, which is 1. Which is what we said it should equal. Now, since it's not in decimal form, it may not be as obvious that they're all less than 1. But if a fraction is greater than 1. The top is larger than the bottom. Like 7/4 is greater than 1. All of our fractions here, the number on top is smaller than the bottom, so they're all less than 1. None of them are negative. And the total equaled 1. This is a probability model. What is the probability of getting a 13? 0, right? There's no outcome on this table that's 13. The probability of impossible events is 0. If there's no way for it to occur, you keep the probability is 0. What about the probability that the sum is between? One and 13. So like 2, 3, 4, 5, 6. This is a 1. Probability of certain or guaranteed events. And one last thing before we take a break and then we go on to like a hands-on activity. Is if. The probability of an event is less. Than 0.05 or 5%. We say it's unusual. This unusual thing is gonna come up over and over and over and over. And over again, and almost every single time, we're using 0.05 as a measure of it. Other than that, let's take a 10-minute break. Alright, so what we were looking at was classical outcomes with dice. There's a game called Pass the Pigs. That's what it looks like. These are the big pigs. They come with smaller pigs, of which I have a bunch. You roll them like dice. So that's what we're gonna do as a group activity. But the way they land is not equal. So I'm gonna show you the 6 different outcomes and the way they land. And what we're gonna have you do is, I don't know, we could probably break up into 6 different groups and give you each. I have got 18 pigs, I can give you each 3 pigs and. You have like someone that rolls and someone that tallies, you do 2 people that tally. And check the tallies afterwards. There are 6 ways that the pigs can land. Side with dot. Is the first outcome. That's where the pig lands on the side and the dot's on top. You'll want this list either on paper or if you're filing it on a computer, that works too. Outcome number 2, side without dot. It's kind of self-explanatory. Then we have the Razorback. That's the move it's called. It's on the point scoring sheet, it's called the Razorback. And it's on its back. Hooves in the air. Or it could land on its feet. If it lands on its feet, it's called a trotter. The 5th one is called a snouter. Snout is another name for your nose. It's where that motherfucker is leaning on his nose. Or rests on his nose. And finally, we have a leaning jowler. Jowler is another name for like cheek, or jowl is another name for cheek. He's on his nose. Nose, 1 ear, and 1 foot. And the rest just fine that way. See how it's perfectly balanced like that? It doesn't do it the other way very well. If I try to do it the other way, it falls. It's usually resting on its left ear.
That's a leaning tower.
Jowler, Jowler, Jowler. They do not fall with equal opportunity. So what we're gonna do is break up into 6 groups. I'll give you 3 pigs. Have one person roll them and announce what they got, the other 2 people tally. And then check your tally, like maybe do it, throw all 4 pigs like 30 times. And then we'll have like 120 pigs from each of you. And we'll see what we get. Don't lose my pigs, please. You're a pain in the ass to get. We got 3 rows there. Marcus, who do you want to group with? Or do you even want to call out? You, are you paying attention? Or do you want to keep working on whatever we're on?
I'm out of it. Tired. You just say.
You wanna join someone, join someone? Jump. Pigs.
We gotta hop in some.
Pigs for you guys. Pigs for you guys. We should work together. Yes.
Where should we go?
Together, you guys just roll them and count them up. Roll them like 40 times so that you have like a whole bunch of outcomes. An easy way of doing outcomes. If you're unfamiliar with the slash method to keep track, 1, 2, 3, 4, and then do a diagonal for the 5th. Makes it really easy to count them afterwards. Spencer, would you like to join one of the people around you?
That's a razorback.
We're supposed to do it as a group, not passing in the 1 pig each. Do it together.
They're pretty excited. Yeah, I just like I'm really on.
Sorry about that. So without thought, it's cool, but you got the thought. I think it's weird. The trotter is the one with where they land on their feet.
On their feet, yeah.
Is there a specific way to drop them?
Just roll them like you're rolling dice.
Alright.
Just try to not go down the cracks and then you gotta go and it does to get them.
Yeah, that's what I feel like. And then don't take it up. So let's go back and do that.
No.
They are not equally probable. You are gonna see some a lot more than the rest.
Okay, that's what I assumed, I was like, I wonder if all like. Equal there, so.
Trotter. Dot dot. Snouter.
Just keep going.
The snouter.
Yeah, just keep going. Let's go for like 10 minutes, whatever you have in 10 minutes, we'll stop.
And tune it out.
Razorback. Two razorbacks and dot. Dot no.
Seems to be the most popular.
You mean trotter? That's the leading.
Yeah, something all over the place.
Trotter, dot. Map. Dot. Razorback, we can go. How many chances have we done?
I'm waiting for this.
Nine times. That's an hour.
Razorback and then Cincinnati.
Two to the. It's an hour.
Yeah, and then 2 dot.
No dots.
And 2 Razorbacks.
I see some smiles.
Nice game of this.
Dots. You know dots. Mix of 10. Oh, do you want 30 outcomes or 30 rolls?
Just roll like 10 for like 10 minutes, whatever you have in 10 minutes, we'll stop.
No dot, all word out. Dot, Trotter.
10 minutes isn't that long for an activity.
Back.
Did I tell you? That was our first whoa. What was it? Was it a jowler or a snouter? They're both kind of rare.
Yeah, the job.
2 dots, 1 dot. Dot, no dot, Razorback. Trotter, Razorback, dot. No dot, 2 dots. Trotter, 2 dots. Trotter, no dot, and then a dot.
Yeah.
2 trotters, 1 no dot. Dot, no dot, so Razorback.
Yeah, I don't wanna throw that.
Snouter, trotter.
No, I tried it like slow. When I try
Razorback, dot, and a dot. Dot, no, 2 dots, 1 no dot. No dot, Razorback. Two moose, Razorbacks, and a dot.
No way.
Snouter, Razorback.
Oh, shit. Oh, look at that. I think it's making them land on that side. Yeah. Yeah, try to. But like they sound smaller.
So shall I?
Try one? For that, for you, for you, just or big.
Yeah. Film appreciation. This box.
Back.
Data science, photo science, tag econ.
We were fucking shaking, I'm like, daddy needs a new fucking car,
Yeah.
maybe.
That's.
Yeah.
Right?
Fucking awesome.
They probably got one on.
Someone's right. I'm on top of the other ones. The other ones are easy. You can't see this one's hard. It's got a lot of work, I guess. I haven't seen it.
Yeah, the battery on it, it expanded and it completely popped the back lid off, it sucks.
Were you like arguing?
Off of a computer?
It's charging. Cause it had just died.
Oh.
A battery just expanded. That's crazy.
Oh, it's from overcharging. I left it on the charger too long.
What is it? A
It was
phone, a computer, or what?
Yeah, it was one of the Chromebooks that I got from high school.
I leave my thing plugged in all the time, not a Chromebook, but my laptop is always plugged in, I know it kills the battery life, but it doesn't. Never had it fucking blow up or get too large.
That's what my dad said, where I showed it to him.
See, it's like.
Now, it might have been where it was kept in the heat faucet.
No, it's chilling in my room, my room doesn't get that hot, I have like 4 fans on.
But if you have it set up where the air is getting to it,
And
the very heat it generates will heat it up. Like it, cause there's electricity running through it, electricity generates heat,
Sure knew.
that's how heaters work, space heaters work.
But it also sucks because I had an ASL test that day too.
Right?
God.
Well, that sucks, period, any day your computer fucking breaks sucks.
I can maybe get another one Friday, because my friend Natalie, she said that she's not using the overall one, so she said she. I was praying I didn't see her right now.
Now back.
I'm going.
Alright, 2 more minutes, then we'll wrap it up. Did anybody get a Jell-O yet?
Yeah.
Or is it waiting on the student?
One little thing.
Can we pass with the pigs?
I'll come get them.
Oh, no.
Holy shit.
Word. Tuesday, Thursday, that's it. Pack it all into Tuesdays and Thursdays so that I can work. This one. Man, 8 in the morning.
Which one, they're on Flurry or?
They're on, the film appreciation classes are on Sunday. So we just watch movies. So I'm joking. Watch a movie. Write what it was
I don't
about.
know how that's a real fucking class, it really dumb.
Then you get all the weird,
W's a W.
you get all the weird theater kids in there.
I wasn't in the class.
Like, I took a music appreciation class when I was here to meet that
Yeah.
category, and there was actually a lot. We listened to music, but there was a lot more like learning terminology and like there's places and shit and.
I watch a movie, he gives us 3 prompts to choose from, and I write 3 sentences about each prompt. Once a week,
Wow,
and it fulfills whatever it does, I don't know.
are you actually watching the movies or?
I actually do, because I personally enjoy the movies, cause after work, I just like to take a shower and go watch a movie.
I have
And
no
then
idea what movies they give you, so they might be lame, you might.
They are totally, they are absolutely lame.
Is it like a documentary or actually?
No, it's a movie, like, we're going through the time period of American film in Hollywood. So we watched the very first movie, pictured movie, and it was from France, that was the very first film.
Like no sound,
No sound, it was only music over the sound. And then, and like they don't pan, it's stationary,
right,
so. It was from 1909.
wow. Alright, let's wrap it up. Should you meet?
Big
stuff.
You did? Okay, I lost round. Drill kicks.
those last few movies, so,
I like that idea.
I mean, at least that's how you gotta do.
it's yours. And he doesn't even pay attention to him, just, I don't even have to go, I can just look up the answers to the prompts,
Yeah, that's true.
which
Humiliating.
I might.
What was humiliating about it?
Words are my mind.
They made up a lot of these names. Learn something. All right. Let's go around the room and figure out how many. Take a second, take a minute, add up what you got. You think we're just gonna make hash marks and not add them up? You gotta calculate probability, it's probability session.
Oh, boy. What's the big pigs about?
The big things were just because they're easier to show.
Yeah, but like, what in the game, what's there about?
It's just a variant that has bigger pigs so that you can let kids play with them without them fucking breaking shit or losing them or.
How do you play the game?
I don't know, I haven't actually played the game, I was going to use it as a teaching lesson. You roll them and like the idea is to, I think, not get, as soon as you get. Dot and no dot at the same time, you lose, you pass through that thing, and then anytime you can stop and add the points that you got, and like bank up.
But if you don't get it, then you have to pass it on to you.
Yeah, as soon as you get a dot and then a no, you're throwing two at a time. As soon as you get a dot and no dot simultaneously, you pass them. Or I think if one's on the other or leaning like they're like interfering with each other, they don't land separately, you pass them, there's rules for passing them, it's. I don't know, I haven't played it as a game. I had to take it home, my wife likes playing these stupid types of games with her family. I'm sure she'll fucking enjoy it. Alright. Who wants to give me the numbers first? You got yours total up, let's go with yours.
26, 34, 23,
What?
oh, 23,
23, okay.
13, 1 and 1.
Yeah, 23 reasons.
Actually, let's go with you guys back there.
58, 48, 40, 18, 3, 1.
Operator, anyone who was at the total?
We got 54, 35, 37, 5, 4, 0.
Next group,
18.
22, 33, and then 2 zeros?
Yeah.
Alright, Spencer, let's hear your humiliation. 30?
I don't think that's right.
10.
I-
5. You guys made this shit up, these aren't rules. You're all easier. These are all increments of fucking 5. God, you didn't, you didn't even try,
I think,
that's even less, that's the lowest number count of them all. You're like, apparently you did find it fucking humiliating.
I think the one where you put 33, I think she meant 3, 3, and then 0.
And she didn't want to say that.
Is it 3, 3, and 0? That's fine. It's, why not correct me if I got it wrong? Alright, let's see how many we got each. What? Let's see, let's add them up, 26 plus 58. Plus 54 plus 18 plus 30. Someone else add these up too, make sure I'm getting the right number. And then I got 34 plus 48. Plus 35. Plus 22 plus 10. +23 plus 40. plus 37, 21 plus 10. Four. 3, 6, 10, 11, and 2. How many is that total? $123. All right, so we're gonna make a probability model with what we got. So we'll make a little table. I'll say outcome. I'll say dot, no dot. Back. Feet. Ear or nose and cheek, how about that? That's shorthand for what we got there. I'll put one with my result. We had 186. 149, 131. 44, 11, and 2 for a total of 523. And now we'll look at the probability of the outcomes. I'm just gonna list them as a fraction first, and then we'll write down the decimal equivalent. You're taking the result and putting it over the total. And let's do these two. I'm gonna say 4 decimal places. Three, 5, 5, 6. Make sure I'm rounding correctly. 0.2, 8, 4, 9. Zero point 2505. Zero point 0841. Zero point 0210. And 0.0038. This is what happens when we do an empirical thing, when the probabilities are unknown, you have to do it this way. Have to do it this way. This experimental or empirical method. So if you look at these as percents. This is 35.56%. 28.49%. 25.05%. 8.41%. 2.1%. And less than 1%. Yeah, if you look this up on Wikipedia. Wikipedia has the following results.
Love Wikipedia. Great source.
We do the same thing with, make the same list. We'll have dot, no dot. Back. Feet. Nose and cheek. Just cause leaning dollar is a long fucking list of things typed to right. Their probability of an event is, they've got 0.302 here. Or 30.2%. No dot. 0.349. Or 34.9%. Back is 0.224. Or 22.4%. Feet was 0.088. Or 8.8%. Nose is 0.030 or 3%. And cheek ended up being 0.0061. Or 0.61%. Now, they did this over 11,954 pigs. So we can actually figure out how many they roll at each. Because we're doing probability equals the frequency over total. That means frequency has gotta be equal to the probability times the total. We were just clearing fractions in the last class, in 321. We can take these, not the percentages, but the decimals. And find out their frequency over here. So I'm gonna do that real quick. So I'm gonna do point, I'll just write out what I'm doing on the first one. Times 11,954. And I'm gonna round to the nearest whole number because I'm sure these percentages were rounded. 3,610 pig, oh, that's up here. And 1194 times 0.349. Oops. This gives me 4,172. Two, six, seven, 8, if I'm rounding to the nearest whole number. $1,052. 359. $73. The reason why I'm saying that is the homework will ask you shit like this. Homework has questions like this. Homework will say. Something like the probability of being left-handed. Is 0.11. If 5,000 people were surveyed. Approximately, how many are left-handed? There's all sorts of questions like this. They're usually multiples of 1,000. They kind of make it easy. What you're doing is you're gonna take the 0.11, multiply it by 5,000. And your answer would be 550 people. What happens if we add our pigs to their pigs? Let's make a new table here. So we got dot, no dot. Back. Feet. Nose. And cheek. And I'm gonna add up the totals of amount here. So for dot, we had. 3,000, or they had 3,610. We had 186. I'm gonna put down 3,796 here. For the total, for the frequency. And I'm just adding our number to their number on each category. Or 1,052. Plus 44. That's 370. And 75. So our total here. Off screen. 11,954 plus 523. 12,477. So let's find the probability of each of these. Shit. We're almost done. All right, let's find our probabilities now. So 3,796 divided by 12,477. I'm getting 0.304 or 30.4%. This is 0.3463 or 346 or 34.6%. 0.225 or 22.5%. .008 to 3 decimal places. Or 8.8%. .030 to 3 decimal places or 3.0%. .0060. So 0.60%. Okay, so. Look at their percentages. And look at our percentages. 30.2, and we added 500 more fucking rolls. And the needle barely moved. Same thing with no dot, 34.9 went to 34.6. 22.4 is 22.5. Razorbacks and Snouters didn't change. And this is off by 0.01%. After 500 plus rolls. If we had only done one more roll. These numbers don't move. This displays a property that, which is how and why we use these proportions to state the probability. When n is large enough. Doing more trials. Barely. Affects the outcomes or the proportions. This is called the law of large numbers. It's an outcome of the law of large numbers. When n is large enough. The short-term outcomes. Short-term proportions. Approach the true probability. Even adding 500 more outcomes didn't move the needle on 2 of them. Barely moved it on this one. And only moved it on the 4th decimal place. And these other ones were all, it changed in the thousandths place. The only changes were in the thousandths place or point something of a decimal. That's why we get to use experimental outcomes as probabilities, even though we don't know, like. Maybe if you rolled it an infinite number of times, we could find the actual probability, but you can't do that, it's not possible. So you just gotta roll, do them enough. And then use that as something reliable. And a good check is always taking the one that is least probable, in this case, the leading dollar. And adding 1 to it and seeing if it changed it. If it doesn't change it hardly at all, you're good to go. Like if we added a 1, just a 1 to theirs here and got a 74. And up this to 11,955. What would we get? 74 divided by 11,955. Is still 0.00618 or 0.0062. It only changes it in the 10,000ths of a decimal place. By adding 1 more pig to this. Total is 11,955. And probability is now 0.062. So when it eventually stops changing the value. And if you do it enough, like if we did have 1,000,000 pigs. We would have more decimal places locked in that don't change. Here, it's locked into. The first 2 decimal places haven't changed, the third one barely changes, if we did like 1,000,000, we might have 5 or 6 decimal places that are not changing. And only the 7th decimal place is changing. At that point, you're like, this isn't changing, the percentage is the same. And it doesn't matter how many more I roll, it's not fucking changing. That's the law of large numbers, we'll do more stuff with this. We'll see how other rules, like how it affects. Gambling, if you like playing Texas Hold'em, we'll talk about how you can calculate getting percentages on hands and shit.
That's pretty badass.
We'll look at how roulette's played and if you, like. Well, some of you don't even know what roulette is, because you're too young and you're getting to the casino, but we'll show you roulette, you'll get an idea for it. Have a good weekend.
Get the fuck out.
Get the, I hadn't said it, thank you, get the fuck out. Now, were the pigs more fun than you thought they
Yeah, it was pretty cool.
I'm not saying that they were fantastic, but they were definitely more fun than you expected, unless you're Spencer. Who felt humiliated. That's a strong word for that.